This video will talk about deriving exponent rules. Before we get into exponents, let's revisit the idea of multiplication. Multiplication is just repeated addition. For example, 4 times 3 means we're doing 4 plus 4 plus 4. We're doing that 3 times. Exponents then are used for repeated multiplication of the base number. So for example, 4 to the power of 3 is 4 times 4 times 4. Exponents are for repeated multiplication. In our example then, 4 to the third, 4 is called the base and 3 is the exponent. And we can expand 4 to the third by writing 4 times 4 times 4. So expanding talks about what does this mean, writing this out. So 4 to the third means 4 times 4 times 4. Using what we just talked about, the definition then for a to the power of n would have a being the base, and then the n would be called the exponent. We can use the example of 4 to the third then to extend this to being any number. We can represent any number with a variable. Oftentimes we call that x. So for example, x to the third just means x times x times x. Use these ideas now. Try to answer the rest of this worksheet. See what you can do. I would suggest expanding each and simplifying to help you discover the rules. Otherwise, let's take a look at number 1. For number 1, we have x to the third, parenthesis, x squared, parenthesis. Remember, when there's no plus, no minus, no divide between your two parts, then it's implied multiplication. So we really have x to the third times x squared. Again, what we can do is expand out what do these mean, and that should help us discover what this answer should be. So x to the third is x times x times x. X squared is x times x. That means we have x times x times x times x times x. Since exponents are again just repeated multiplication, how many times did x happen? We say that's x to the 5th power. Looking back then, we had x to the third and x squared. You might want to ask yourself, how can I use the 2 and the 3 to have gotten 5? What could I have done with the exponents? We see then that I actually could have just added the exponents. So in general then, when we're multiplying by the same base, meaning both of these were x's, they had to be the same, what can we do with our exponents? We can just add them. That means a to the power of n times a to the power of m would be a to the power of n plus m. On the next problem, since anything to the power of 3 is really just multiplying whatever is inside the parentheses 3 times, we ask ourselves x to the third squared. So x to the third is inside the parentheses squared. What would that answer be? Take a moment, try to expand that out, see what you get. Otherwise, we get x to the third times x to the third. That's being multiplied 2 times. Again, whatever is inside the parentheses is being multiplied 2 times. We just saw in the previous example then, when I'm multiplying by the same base, what can I do with my exponents? Just add the exponents, so this would be x to the 6th power. I also showed you expand out, the x to the third is x times x times x. The other parenthesis of x to the third is x times x times x. We see I'm multiplying x 6 times, that's again why we get x to the 6th. We should now ask ourselves, hey, how can I use that 3 and the 2 to get 6? What kind of operation might I have to do that? And we see here that when I do a power to a power, I actually have to multiply. So a to the power of n, and that whole thing to a power of m. So when I have that power inside a parenthesis to another power, that's a to the power of n times m. We multiply exponents when I do a power to a power. Let's use the fact then that a to the power of n to the power of m multiplies a to the power of n m times to answer the following. Again, we want to expand this. So on the very first problem here, for number 3, we have parenthesis negative x parenthesis squared. What does that mean when I say this whole thing inside this parenthesis is squared? It means we're multiplying negative x twice. We see a negative times a negative is a positive. That means my answer would be x squared as a positive. On the next problem, I have negative x inside the parenthesis, this time to the power of 3. Again, expanding that out means I have negative x times negative x times negative x. A negative times a negative is a positive, times another negative means my answer here is a negative x to the third. Take a moment and try to expand out the parenthesis negative x parenthesis to the fourth, and parenthesis negative x parenthesis to the fifth. Otherwise, here are those two answers. We see that parenthesis negative x parenthesis to the fourth gives me a positive x to the fourth. The negative x inside of parenthesis to the fifth power gives me a negative x to the fifth. Let's take it a step further then and look what happens when I put the negative inside the parenthesis on this first one versus outside the parenthesis versus no parenthesis at all for being both a even and an odd. We already saw on number 3 that parenthesis negative x parenthesis squared is positive x squared. Again, whatever was inside the parentheses is being multiplied twice, so that's why we had negative x inside of parentheses happening twice. On the next problem, we have negative parenthesis x parenthesis squared. Again, this means that whatever is inside the parentheses is being multiplied twice, and I still have this negative in front. So this actually gives us a negative times x times x. X times x is x squared. This negative, you can really think of it almost like having a negative 1 in front of it, which gives me a negative times a positive, so that's how I get a negative x squared. For the next problem, we have a negative x to the power of 2. Order of operations tells us that I have to do exponents before multiplication. Because remember, this is kind of like having a negative 1 in front of the x squared, which gives us negative x squared. Take a moment and try to do the negative x to the thirds with the parentheses in the different spots. Otherwise, here are those answers. We already saw the parenthesis negative x parenthesis to the power of 3 in number 3 up here. So again, that was just negative x times negative x times negative x because I was inside the parenthesis happening 3 times, which gives me negative x to the third. For negative parenthesis x parenthesis to the power of 3, remember that's really kind of like saying negative 1 times x times x times x, because the x is the part that's inside the parenthesis happening 3 times. Negative times a positive times a positive times a positive is negative x to the third. And the negative x to the third order of operation says we do the exponent part first, so that's the x to the third part, times that negative 1 gives me negative x to the third. Using our examples from number 3 and number 4, should hopefully be able to generalize and say that when I had a parenthesis negative a parenthesis power of even, which looks like the first and third examples from number 3, that gave me a positive a to the even power. However, when I had a negative outside of the parentheses to an even, or just a negative without parentheses of a to the even, both of those, as we saw on our number 4 second and third examples, that gave me a negative a to the even power. Looking at the odds from our second and fourth examples of number 3 and the last 3 examples of number 4, all of them, no matter what, whenever it's an odd power, if it's a negative, we'll end up staying negative. So again, big ideas. If we have a negative to an odd power, it's going to be negative no matter what. If we have a positive to an odd power, then it's going to stay positive. If we have an even exponent, then when it's a negative, if it's inside parentheses, it becomes positive, but otherwise, if that negative is outside of parentheses or no parentheses with that negative, then it stays a negative when I have an even exponent. Now let's look at what happens when we divide bases. Before we get into that, let's revisit. What is 4 divided by 4? That's 1. What's 7 divided by 7? That's also 1. Therefore, x divided by x is 1. Anything divided by itself is 1. Well, almost anything. We'll get into that idea in a little bit. So remember, x divided by x is 1. We'll say that it cancels, but really we mean that it actually equals 1. So using the fact that x divided by x is 1, we'll say that it cancels, but remember it actually means 1. Let's try to answer the following. When we multiply by the same base, we add exponents. That's what we saw before. Now, what do you think happens then if I divide by the same base? What should I do with my exponents? Let's expand and see if your idea is correct. So x to the 5th power is x times x times x times x times x. X squared is x times x. Remember, what does x divided by x equal? 8 equals 1. Again, we'll say that cancels. So what happens is we get x divided by x canceled, x divided by x canceled. I'm left with x times x times x, or x to the 3rd power. We see from my exponents that really then all I have to do to get to x to the 3rd is actually subtract my exponents when I'm dividing by the same base. So in general, when dividing by the same base, we subtract our exponents, which means a to the power of n divided by a to the power of m is equal to a to the power of n minus m. And number 7, take a moment and try to do x to the 6th divided by x to the 5th. What do you get there? Otherwise, here's the answer to that. We see that my x to the 5th cancels 5 of the x to the 6th, leaving just x. Again, I'm subtracting. We just saw that on the previous example that I subtract when I'm dividing by the same base. So 6 minus 5 is x to the 1st. Note, we do not write x to the 1st, we just write x. That 1 is implied. So, any number to the power of 1 is really just itself. Therefore, a to the power of 1 is just a. So what happens when we divide by the same base with the same exponent? For example, x to the 5th divided by x to the 5th. Take a moment, try to solve that and see what happens. Otherwise, here's what you get. As an expansion, x times x times x times x times x on the numerator. Same thing on the denominator. X divided by x cancels, giving us everything canceled. What does that mean? Remember, when it cancels, it means 1. So this actually equals 1. Since I'm dividing by the same base, I can subtract the exponents as we saw on number 6. So let's use that same idea. So we have x to the power of 5 minus 5. 5 minus 5 is 0, so x to the power of 0. But since these are the same, this means that x to the power of 0 is 1. This is the reason why we say then in general, any number to the power of 0 is 1. So a to the power of 0 is 1. This implies any number to the power of 0 is 1, which is essentially true except for one special case, and we'll talk about that here coming up in a little bit. Let's extend this now. What happens when my numerator is not bigger or equal to my denominator? What happens when my denominator exponent is actually larger than the numerator exponent? Take a moment and try to solve these 3 problems. X to the 5th over x to the 6th, x to the 5th over x to the 7th, and x to the 5th over x to the 8th. You should have gotten these answers. Notice that when everything cancels, my numerator can still be multiplied by 1, because 1 times anything doesn't change it, right? It's still the same. So I really have 1 over x. So when you have a negative exponent on the numerator, notice that it moved to the bottom. Here I had x squared left over on the bottom. There's more x's on the bottom than the top. That's why the x's are on the bottom. It is not a simplified answer until we have positive exponents. We never leave this as negative exponents. So if it is a negative exponent, move it to the other side of the division sign. Thus, a to the power of negative n is 1 over a to the power of positive n. Note, this rule just says that it moves to the opposite side of the division sign. Not always necessarily going to move to the bottom. So here are some extensions of the rules of exponents then that we need to address. Take a moment and try to figure out number 10, 11, and 12. We have 0 squared, 0 to the negative 2, and 0 squared divided by 0 squared. See if you can figure out what you think those answers are going to be. Otherwise, here's what we should have gotten. Since 0 squared literally means 0 times 0, 0 times 0 is 0. Looking at 0 to a negative 2, remember we just saw that when I have a negative exponent, it moves my base to the other side of the division sign. Since at the moment, anytime you have a number, it's really over 1, this would move my 0 to the bottom and become 1 over 0 squared. No, we didn't flip the fraction here. Couldn't have just written over 0 squared. I have to have something in the numerator here, so I can always have 1. There's always a 1 there, right? Because 1 times something is itself. So that's why there's a 1 at the top. You can't just have over 0 squared. Remember, when you move your negative to the other side of the division sign, it becomes a positive exponent. Now I'm asking myself, 0 squared, we just talked about 0 squared. 0 squared is 0, so I really just have 1 over 0. So what is 1 divided by 0? Well, that answer is undefined. The last scenario we have for the 0 is 0 squared divided by 0 squared. Remember, when I'm dividing by the same base, I can subtract the exponents, so this would give me 0 to the 0 power. Remember, we also though talked about the fact that 0 squared is just 0, so 0 squared divided by 0 squared is actually equal to 0 divided by 0. Now, while there's a little bit of debate about what this should equal, and different contexts make different answers seem more reasonable, we cannot divide by 0, so we're actually going to call this undefined. Take a moment and fill in then our 0 to the positive, 0 to the 0, and 0 to the negative. What did we discover? Well, we found that 0 to a positive is just 0. 0 to the 0 power is undefined. And 0 to a negative power is also undefined. So note, anything to the power of 0 is 1, except if the base is 0. So when we say that phrase, it's actually implying that a does not equal 0. So we don't write it, but it is implied. Oftentimes we don't talk about special cases. It's good to note, but after you've noted them, we typically don't talk about it again. Now let's try number 13. That says x to the third times y squared. What do we think that answer is? Well, that answer here is actually the same exact thing. It's the same exact answer because we can't combine them because they have different bases. You can only combine your exponents when your bases are the same. So that's our general rule here. On number 14, we have parenthesis x, y, parenthesis to the power of 3. This one is trying to show that we are multiplying x, y 3 times. And because multiplication is associative, we can put our x's together and our y's together into parentheses each, which shows that we get x to the third times y to the third. We don't have to use parentheses, the multiplication is implied. It should also be noted that if we had a number, the number needs to be in front of your variables. With coming back to then the original problem, parentheses xy, parentheses to the power of 3, the exponent for x to what power gives me x? That would be to the first power. Y would also be just to the first power. We saw in problem number 2, when I do a power to a power, that we multiply our exponents. The 3 is going to get distributed to both parts, and that's what gives me the x to the third, y to the third. In general then, we distribute our exponent to the other exponents inside the parenthesis by multiplying the exponents of each part. On number 15, we have x over y to the negative 3. This answer will become x, y to the third power. The x doesn't move because remember, x to what power gives me x? It's just x to the first power. So big idea here, we only move negative exponents. Positive exponents stay in the same place after we've simplified everything. If you haven't done so already, try number 16, which is parenthesis x over y, parenthesis to the power of negative n. Otherwise, this is what you'll get. Y to the power of n over x to the power of n. You can distribute the negative n to the top and bottom. So I have x to the negative n over y to the negative n. The negative exponent moves it to the opposite side of the division sign, so anything at the top that's got the negative exponent would move to the bottom. Any negative exponent on the bottom would move to the top. Or the negative you can immediately flip. So remember, it flips everything. And then from there, distribute my n to both the numerator and denominator. So our generalization of this is quantity of a over b to the power of negative n will just become b to the power of n over a to the power of n.